We are going to be looking at a generic heating curve. And with these heating curves or cooling curves, we're just looking at the trend of a substance undergoing a phase change. That means it's changing from one state of matter, solid, to another, liquid, through a phase change like melting or freezing. We are not worrying about the specific temperatures at which these occur at, but we just want to see what that general trend is. And then we are going to look at how much energy either needs to go into or release from these phase changes to allow these to occur. Solids have molecules that are tightly packed together based off their forces of attraction. This could be for our ionic compounds with their electrostatic attraction between the ions, our molecular compounds using the intermolecular forces, dispersion forces, dipole-dipole, or hydrogen bonding, but they all are going to create solids. Here I have ice water or solid water, and it is going to arrange those molecules, those water molecules, in a crystalline lattice formation, maximizing the amount of hydrogen bonds between each of those molecules. Our solids, our atoms, our molecules are still vibrating in place. We are not saying that they have zero energy, it's just that they are maintained in a rigid form. But as we heat up that solid, these molecules start to vibrate faster and faster. So as we start vibrating faster and faster, we're going to start to weaken those hydrogen bond interactions that are occurring. Now, because we are heating something up, that means we are having to put energy into the solid. So this is an endothermic process. We can look at this heating of a solid as a temperature change occurring within the solid itself. We have not changed phases yet. So we have this calculation MCAT. So Q stands for the heat. So this is kind of like delta H, but we're not talking about energy per mole. This is just the heat evolved in this phase change, so it's based off mass. So Q is the heat in calories or joules that is going to be released if you are cooling off, or absorbed if you are heating up. The M represents the mass of the substance that needs to be heated. The more mass there is, the more energy is going to be required to heat that mass. The C stands for specific heat capacity. Every substance has its own specific heat capacity at its solid, liquid, and gaseous state. So specific heat is the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius or Kelvin, and it represents the thermal property of that substance. We can use specific heat to understand how fast or slow substances heat up. So if you think about the handle on a pot or a pan, it is made of a different metal typically than the pot or pan itself. We want the pot or pan to heat up quickly so it can cook our food, but we don't want the handle to heat up quickly because we're going to be touching that. So those metals have two different specific heat capacities. These numbers are given to us, not that we're having to calculate it, but we just want you to have this understanding. The delta T represents the change in temperature. So negative 10 degrees Celsius up to negative 1 degree Celsius is a change of 9 degrees Celsius. Now, water specific heat is 0.50 calories per grams degrees Celsius, which is different than its liquid specific heat and its vapor specific heat, which we will get into. Once we've heated up the solid enough that we start to disrupt those intermolecular forces between these solid ice or water particles, we are going to hit our first phase change. So going from a solid to a liquid, the phase change process is melting. The temperature at which this occurs is called the melting point. If we're talking about water, solid water starts to melt at 0 degrees Celsius. That is when it has enough kinetic energy to start to disrupt those intermolecular forces, changing how those molecules are moving and are associated around each other. We can also quantify this as the phase change. Q is still the heat calories or joules. M is the same mass that we were working with. HF is our new variable here, and HF is called the heat of fusion. This value is specific to water. This is a measurement of the amount of energy needed to disrupt the intermolecular forces to allow the water to start to slide past each other and how the liquids work. This is a measured value at 80 calories per gram. The phase change takes more energy than a temperature change because temperature change is looking at mass, and yes, we have a specific heat, but it tends to be a very small number, and the change in temperature tends to be smaller. But in a phase change, it requires a lot more energy to get those molecules to start to separate. Once we have started to disrupt the number of hydrogen bonds between the water molecules, we have now converted to our liquid state. So this is what we mostly understand and know is when we put a pot of water onto the stove, it's going to start to heat up. This takes a lot longer because the energy needed to go from a liquid to a gaseous state is significantly larger because you have to completely disrupt the intermolecular forces present there. So in a liquid state, there are fewer hydrogen bonds between those water molecules. And because this is a temperature change, it is the same calculation as we saw with the solid. The difference is the specific heat. So the specific heat for liquid water is 1.00 versus for the solid was 0.50. So that tells you that liquid water can absorb and hold more heat. It takes more energy to heat up liquid water than it did solid water. So once you hit that point, again, going with our pot of water, and you start to see those bubbles coming up, we are hitting that next phase change. So this next phase change is where we are vaporizing the liquid into its gaseous state, or its vapor. The temperature at which this occurs is the boiling point. So water at sea level boils at 100 degrees Celsius. Here in Colorado, it's typically around 93 degrees Celsius because we have less atmospheric pressure, so it boils at a lower temperature. Now, when this is happening, the molecules or the hydrogen bonds between those molecules are starting to be completely disrupted. So we are now going from this flowing of forming your hydrogen bonds and then releasing, forming, releasing, kind of staying together, to completely disrupting, preventing any hydrogen bond formation. So this phase change is called Q equals mHV. HV is the heat of vaporization. Note that the value used for the heat of vaporization for water is significantly higher than the heat of fusion because we have to completely disrupt the hydrogen bonds between the waters in order to transition from the liquid to gaseous state. And that just takes so much energy in which to pull it apart. That also kind of gives you an idea of how strong hydrogen bonds are between water molecules. Imagine that instead of letting that gas or that vapor boil off into the atmosphere, we have a closed container. So we are capturing this gas. Don't do it. Pressure, dangerous. We'll learn about that in gas laws. But if we were to be able to capture that gas and continue to heat up that gas, you would see again a temperature change occur with the gas itself. You'd see that temperature to continue to increase. We don't typically do that. We tend to stop at that vaporization as we're working with open containers. But in theory, we can see that gas would also have a temperature change. So when we are talking about, is a steam burn worse than a boiling water burn? The answer is yes, because a steam burn is going to be absorbing or releasing this 540 calories per gram of the water, whereas this boiling water, it's going to be at that one temperature in which it was boiling at for that same mass. But the number here is going to be significantly smaller than the 540 because our water doesn't boil at 540 degrees Celsius. And so steam burns are significantly higher risk. There's a larger energy transition than when we have hot water. And we can say the same thing with a freezer burn. You can get burned by a substance that is freezing, because again, it is going to be absorbing or releasing more energy than we would see in that temperature change of a liquid to the solid state. The last endothermic process we want to talk about is sublimation. Sublimation is when we have a solid that skips the liquid state and goes directly to a gas. We don't worry about calculating this because you have to take pressure into account as temperature, but the most common product we know that undergoes sublimation is dry ice, so CO2. So that CO2 is kept under pressure in a very cold freezer, and that allows it to maintain its solid shape. But as soon as we open that freezer, the pressure changes and the temperature is significantly higher. That CO2 skips its liquid phase and it goes straight into its gaseous phase. All right, so we looked at the heating process, or the heating curve, which is the blue arrows going up. We can also have a cooling curve. So we are taking a gas and it is going to condense through the phase change of condensation to a liquid. The phase change calculation stays the same. It's just that Q value is either positive or negative. It's just like our delta H. So a positive delta H means it's an endothermic process. So vaporization would have a positive Q value. Condensation would have a negative Q value because that's an exothermic reaction. In order for a gas to become a liquid, it has to release that kinetic energy that it's moving around. It's got to slow down so that those hydrogen bonds can start to reform. In order to do that, it has to release energy, and that is why it's exothermic. So this is our condensation point, or what we would call our dew point, like in the morning when the water in the atmosphere appears as dew on the grass. Our liquids can be cooled through that temperature change, again, exothermic, because they need to slow down. And then we can get to that freezing point. And that freezing point is still that phase change, heat of fusion. It has that same value, so it's the amount of energy that needs to be released in order for the molecules to become a crystalline structure. And then our solids can continue to decrease in their temperature as well.